Okay, welcome back, electricity and magnetism students. So you already saw the video on the point charge review, and today we're just going to look at this concept organizer that I handed out to you earlier in the year. That's going to be the focus of today. And the reason why is I took a lot of time here to put all the four main ideas in electrostatics together on one sheet, show the basic, most important parts of what each concept is, and then also how they relate to each other. As I said at the start of the year, these four ideas are the four ideas that are behind more than half the curriculum of the course. So if you don't have these down solid, then you can basically what that means is you're going to struggle in topics like capacitance, capacitors, conductors in an electric field. All those topics we studied will be difficult for you. Gauss's law, okay? So what are these four ideas? Well, as I mentioned in the first video, there's force, electric field, electric potential energy, and electric potential. On this side, the force and the electric field, these are vectors. Okay, what that means is direction matters. Okay, so that also means you do not plug signs. If there's a negative charge, you don't plug in the negative in these formulas. The negatives and positives are to help you figure out, or to allow you to figure out the directions of the forces involved or the directions of the electric field. So, like in this little simple example, you see, I want to find the net force on this charge. So, this positive repels away this positive, like charges repel. But this negative down here attracts this positive. So that's how the minus, what it told me is that this arrow goes down instead of up, being a repulsion. But when I plug the values of Q1, Q2, and Q3 in this formula, I put in the positive absolute value so that I get the force, the length of these arrows. And then to find the net force, because these are vectors, I've got to use the Pythagorean theorem in this case. But you might use the law of sines, you might add components, whatever you're doing, you have to add them as vectors, not as scalars. Like if this is 2 and that's 1, the answer is not 3, right? You got to use Pythagorean theorem. The electric field, basically to figure out the electric field from force, you would divide by Q here, F over Q, the newtons per coulomb. That's also vector, which means, as I said, you don't plug the sign in the formula. It points away from positives, electric field, and it points towards negatives. So here's another little example. If I wanted to find the electric field here, caused by these two charges, this positive makes an electric field point away, this negative towards itself. And then I have to use some kind of vector sum. In the upper right corner here, we have electric potential energy. U, right? Gravitational energy, we had U. Electrical energy, we have UE instead of UG. KQQ over R. This is a scalar. First of all, the definition is the amount of work to bring Q2 from an infinite distance to Q1. So, if I had one object here, and let's suppose I have a second object, and I figure out KQQ over R, those are supposed to be point charges. Let's suppose they're both, point charges instead of a box and a bolt. What does that answer tell me? It tells me the amount of work to bring this from outer space all the way in to that point. Okay? So that's the work, technically the negative work done by the electrostatic force coming from infinity in. That's the key idea. You have to realize it's from infinity into a point where you are away. Again, it's a scalar. That means the sign must be plugged into the formula. So you do put negatives in there. And the total energy is just found by adding. No Pythagorean theorem, no sine or cosine, none of that when you add up the total potential energy. But the way you get there from force is it's the negative integral of force dx from one coordinate to another. So I kind of already mentioned that. So if you have force, you have to integrate to find the potential energy. If you have the potential energy as a function, you have to take the negative derivative to figure out what the force is at a particular point. Okay? And lastly, down here in the corner, electric potential, in other words, voltage. It's called potential in physics problems very often, not really voltage. So what it is, the definition is it's the amount of the charge's electric field accumulated. I put that in quotes because it's a rough conceptual idea, but it's accumulated along a path from infinity to a point, a distance r from Q. Accumulated, what I mean is like you're integrating from infinity into a particular charge a certain distance away. So if this is the charge, maybe it's a proton, electric field points away. We'd integrate coming from outer space the whole way until we got to a particular point. When you plug in kq over r, that is the answer to the integral coming from outer space, infinity, into that point. So that's what I mean by the electric field accumulated along that path. Voltage or potential is also a scalar. That means it's a number, it's not a vector, it doesn't have a direction. No arrows. And that means you could just find the total voltage or the total potential by simple addition, with minus signs included, of course, so maybe you're subtracting. So then the way, if you want to find the electric field, if you have the voltage as a function of x or r or whatever, you have to take the negative derivative to find the electric field. So integrate here, take the derivative there. So there they are, the four main ideas, how they relate amongst each other. Study this, know these, okay, firmly in your mind, and then that'll make the rest of the topics more manageable. Okay, see you in the next review video.